group called gamma n, and it's just the kernel of the map from PSL2Z to PSL2 Z mod NZ. So this is the homomorphism which replaces a matrix with integer entries, where I consider those entries modulo n, still a group even though Z mod NZ is not a field or anything, unless n is prime. So you can think about these as being matrices of A, B, C, D, and I ask them to be congruent to plus or minus the identity mod n. The sign is annoying, I realize. So the gamma 1 would recover my PSL2Z. There's an exact sequence which so realizes that gamma n is the kernel. It turns out that this map is surjective. We don't need that today, but if you want to think about why that map is surjective, you should certainly think about that. Usually people say strong approximation as a way to scare you, but it's really the theory of elementary divisors. Okay? A group is congruent if it contains one of these guys. So gamma, a subgroup of PSL2R, is congruent if gamma contains gamma n, or some n. The minimal n is called the level. If it is congruence, what are our favorite congruent subgroups? Well, they come with jazzy names like gamma 0 and gamma 1. Sometimes we fail to be more creative than that. So be it. So these are the ones where I get to pick something that is defined by congruence conditions. That's why they're called congruent subgroups. And instead of requiring it to be the identity, I take things that are upper triangular or unipotent. So see if something looks like this. So the stars mean you can put anything there. And here, this is congruent to plus or minus. You probably can. Sorry about that. And here we say 1, 0, star. Okay, so what are the S and T for this group? Well, maybe we need more generators. What happens when you fold a fundamental domain along with the gluing relations? What kind of surface do you get? What does it look like? That's the goal. Okay. Let's do an example. Gamma 2. I'm going to show you what kinds of things we would be hoping for answers. So gamma 2 has a fundamental domain, and it actually looks like this. Sort of advanced theory. Instead of doing it once to your homie in the street, you do it twice. So this is the map which is given by a double translation. And there is another element here which pairs these two sides together. And beautifully and symmetrically, it is this matrix. Instead of upper triangular, it's lower triangular. Yeah, question?
For the definition of congruence group, do you assume gamma in PSL2R or PSL2Z?
I don't assume that it is PSL2Z, but it happens to follow as a consequence of the definition. Okay, so think about why that's true. That if I try to throw in a square root of 2 there or something, that's not going to allow. So I guess I need to say something like, what is gamma? Gamma is a floating symbol, doesn't mean, what is gamma wants to be a subgroup of PSL2R, but in order for anything to be interesting, it needs to be a discrete subgroup. Okay? So I guess I could make this definition for non-discrete groups, but it's not going to be that exciting. So this needs to be a discrete. Okay? So my gamma 2 looks like this. Turns out that these guys generate gamma 2. Okay. What happens when you fold this guy together? Well, there's a point at infinity here. There's 0. There's -1. There's 1. Okay, so it looks kind of like the original snack treat, but now I have these points there. So if you want to think about it as a topological surface, you might blow into the corn chip to make it look like a sphere, but that sphere is missing 3 points. Okay? But you might ask, isn't that lovely? Have you seen this before? Some of you I know have, because you're not students. Were you actually in the end able to prove that these generate and to get fundamental domain? It's not clear. They moaned pretty hard about it. The ST proof doesn't translate quite as readily to this situation. You might try to do this with your bare hands, but you should be asking me, why? How do you get this? That seems too nice to be true. How does that really work? Okay? So I need to give you a method for producing these kind of things. Okay, one other name, because these are going to pop up. What do we call these points that are missing from the glued together surface? We call them cusps. So cusp, what's the definition of a cusp? It's the orbits of gamma on the boundary. We don't have to take all of P1 of R, so R union infinity. We just need to take the gamma orbit of infinity, if we think about gamma being PSL2C, so all, and then up to gamma equivalents. Okay, so it's maybe just simpler to think about P1 of Q, which is Q union infinity, and I ask for the gamma orbits of that. So if you think about rational numbers or pairs of co-prime integers, and you have PSL2Z act on that set, that's P1 of Q, and then I ask for the gamma orbits of that. And because the congruence condition is imposed on gamma 2, I'm apparently able to write any such rational number as either infinity, 0, or 1. Okay, that's the point of having those cusps. So we might want to know also for other groups, what's the set of cusps? All right, I keep promising things. I guess we better actually get started now and do stuff. Feel like we've been doing things, but mostly for motivation. Here we go. They're called fairy symbols. So this is the sort of combinatorial amazingness. Have you guys seen the fairy sequence before? The original fairy sequence is a way of listing the rational numbers in order. So you ask for, among the set P over Q, I guess you have to decide whether you want to include 0 and 1. I will. Okay, any rational number you can write like that. They're between 0 and 1, so I'm going to write P and Q is both positive. QQ is not 0. But I ask the denominator be less than n. You list them in increasing order. What does this have to do with the upper half plane, you ask? Well, hold on. Okay, I'm rebooting a little bit. This is a set. What is it? How does it start out? Okay, well, when n is equal to 1, here's what it looks like. And that's n is, I guess, 2, since I'm taking it strictly less there. Yeah? Okay, what comes next? To me, like I'm going to have this. I left a little space there. What about n is equal to 4? Here's what it looks like. Is it clear what this set is? So for every integer n, positive integer, I list the rational numbers between 0 and 1 with denominator at most n in increasing order. Okay, I get a sequence. I'm writing it as 0 over 1 to emphasize something. Okay, now do you notice any patterns in this sequence? So if I were to keep, I left a space here so that we could see one of the patterns, but maybe we'll just try to visualize it here. It looks like how do I make, if I have the fairy sequence at level n and I want to make the fairy sequence at level n plus 1, I could just write it down. There's no one's going to stop you from doing that. But after a while, you want some more coherent way to produce the next sequence of rational numbers. Do you guys notice any patterns here?
Denominators are symmetric.
There's definitely a symmetry between, yeah, so you could list them up to the halfway point, and then by symmetry, you have to, listing up to there, and you subtract from 1 or add. So that's evident, okay? But do you notice anything else? Yeah. Isn't that kind of weird? Okay, I'm going to make a new rational number by taking these two in the previous level and adding the numerators and adding the denominators. Okay, now this is sometimes called in a derogatory sense, fresh person addition of fractions. First, you know, someone ever asked you to add fractions, and you were really, when you were a kid, why not just add the numerators and add the denominators? What's so wrong with that? Okay, if you try that, well, you don't pass your 5th grade or whatever. Okay, but here, that's what we're going to do. It's a new operation on fractions called add the numerator, add the denominator. Okay, now amazingly, that's exactly what you need to make the Ferry sequence. Okay, because for example, if I do that here, well, I always have 0 and 1 on the outside. Okay, but if I take 0, 1, 1/2, you see how I get this fraction? And then if I do the same thing with this one, I get the 2/3. Okay, so I also have to, I guess, stick in the 1/2 in the middle, but I knew that that one was coming. Okay, so this is called the Frosch's sum of fractions. Okay, let's make up a symbol for fun. So if I take two fractions, a over b and c over d, and I frosh them together, it sort of looks like a plus, right? Okay, let's be slightly more sophisticated. We'll call this the mediant of the rational numbers a over b and c over d. Okay, everyone follow that so far? Okay, so the connection to the Abrahamic plane is still distant, but coming back. So I need one lemma that I encourage you to prove yourself. That says that this really works. Okay, so we say, so if I take two such fractions, I say they're Ferry neighbors if they are adjacent to each other in the Ferry sequence, okay, for the integer n. So these are if and only if. Something that looks like a determinant, but it's the negative of the determinant. Okay, and then the statement is continuing. If you take the mediant between the two, and there's an induction that you can get from this as well. So if I call this fraction in the middle h over k, then I still retain this property. So in other words, is the statement clear? Maybe some of you are still scribbling it right down, but it's saying that the way to generate the Ferry sequence is by using the mediant of the fractions in the previous line. I can detect if two things are neighbors by this determinant condition. If I take a mediant, then this says that the mediant between the two again satisfy those conditions, so therefore they're Ferry neighbors. And that tells me how to generate the entire sequence. Okay, it also indicates the provenance of this hypothesis and what you might try to do to prove it. There's so much to say about the question back. Nope, just scratching. All right. There's so much to say about this. Maybe I'll leave those conversations to other exercise sessions or whatever the other hours that we have with ourselves to discuss other mathematics. Very simple. How am I doing on time? I'm going to take 5 more minutes because we started late. Is that okay? Brad. Thank you. So I need to make 2 definitions, and then I'll make a statement, and we'll we'll prove the statement starting next time. So it's all for motivation. It's a good start on Thursday. So first of all, we'll define a generalized Ferry sequence. This is a sequence of fractions x0 equals a0 over b0 is less than dot 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 is less than an over bn, which is xn. I asked for those fractions to have the property that the GCD of numerator and denominator is equal to 1 to avoid trivialities. I always write my fractions with positive denominator. And I asked with consecutive terms satisfying this Ferry condition. Okay, so I'm not going to write an AI and BI because I want to write it like this so that it really looks like the thing we had over there. Okay, so this is BI, AI plus 1 minus AI. Okay? So a generalized Ferry sequence is not the Ferry sequence, but I take some of the terms in it, and I require any two terms next to one another to satisfy this Ferry condition. Okay? So we extend to include infinity, which we're going to need. So we write minus infinity as minus 1 over 0. Infinity is 1 over 0. So you have to squint a little bit to think about that. So these are, I made the definition of a generalized Ferry sequence, and I also need to allow myself the symbol minus infinity and the symbol infinity. Minus infinity is less than any rational number. Infinity is greater than any rational number. I always write them as minus 1 over 0 and 1 over 0, and I still can ask for this kind of condition to hold. A Ferry symbol is a generalized Ferry sequence starting at minus infinity ending at infinity and together with a bit of extra data. This data is just labels between the pairs. Okay, so I made the sequence, rational numbers satisfying the Ferry condition. Between any two of them, I'm going to put some decoration. Okay, I have three options for my decoration. Those options are called free, odd, or even. Sorry, not my choice in terminology. I'm just borrowing from what was used before. So if it's free, I label it with a positive integer. And if it's odd or even, I have the symbol black dot or open dot. And the only other condition is that each of these positive integers only appears twice. And it always appears twice. So it either doesn't appear, or it appears, and it appears exactly twice. It does not have to be always symmetric in that way. You can label them however you like. So each relabel appears exactly twice. If you guys are still with me, the thing I want to end with is there exists an algorithm that takes as input one of our groups gamma. Doesn't need to be congruence. It will focus on the congruence case, but I just need this to be finite index. Takes as input, and it produces as output a certain kind of Ferry symbol. fairy symbol for gamma. Okay, and this fairy symbol gives us all of the things that we want. So it gives us an encoding of the fundamental domain. It gives us labeling for the edge pairings, for the side pairings, and it tells us the cusps. It gives us a reduction algorithm. It gives us everything that we might hope for. Okay? So I have to explain this algorithm to you, and I will next time. I hope you can wait that long. If I've piqued your excitement to the maximum. Maybe for fun, I'll tell you what the fairy symbol is for gamma as PSL2Z. And then we'll be done. It's called minus infinity is less than 0 is less than infinity. And along this edge, there's a black dot. For this one, there's a white dot. This is supposed to tell you, for example, that the cusps minus infinity and 0 and infinity are identified. So the rational numbers that appear are the cusps up to the pairings that are there. So there's only one cusp. It's called infinity. And even better than that, there's a way of thinking about the fundamental domain as being derived from these symbols with the gluing relations evident. From here you can read off the stabilizers of the points of order 2 and 3. I don't know, maybe we'll have some time to talk more about this today, but if not, next time. All right, thanks guys.